Hello everyone. The title of this video is Graphing Parabolas with Vertices Not at the Origin. Alright, so in this video I'm going to be going over examples that are taken directly from a free online textbook at openstax.org. I'm in their Algebra and Trigonometry text, section 12.3 called The Parabola. And I'm under the heading Graphing Parabolas with Vertices Not at the Origin. And the examples I'm going to be doing are either examples from the reading, or one of the try it problems from the reading, or one of the exercises at the end of the section that's related to this particular objective. Alright, so I'm going to be assuming that you've seen my video or read earlier in this section about graphing parabolas with vertices at the origin. Because the only difference is there's a shift. The origin shifts to the point hk, and to do that you take the equation in standard form from earlier when the vertex was at the origin, replace the x with the quantity x minus h, replace the y with the quantity y minus k. So we get these two standard forms here, right? One has y squared and not x, right? And those were parabolas whose axis of symmetry was horizontal. And the other one has x squared, not y. And those were parabolas whose axis of symmetry was vertical. And then we had to find this point, a special point called the focus, a special line called the directrix, and a special segment called the latus rectum, which was a segment containing 2 points of the parabola and the focus, and was parallel to the directrix. Right, all that stuff I'm assuming you remember from, again, my video on graphing parabolas with vertices at the origin. And there's a little box here going through a bit, showing you these standard form equations. See, when the axis of symmetry is a horizontal line, you have y minus k squared equals 4p times the quantity x minus h, right? Some number 4 times p times a quantity x minus h. And when the axis of symmetry for the parabola is a vertical line, x equals h here, the equation, you just switch the x minus h and y minus k. It's x minus h squared equals, some number 4p times y minus k, the quantity y minus k. And, if you know the value of p, and that the vertex will be at the point hk, and when you know the value of p, that'll tell you how to get to the focus, right? The focus will also be on the axis of symmetry, as you see in all these pictures. The focus is on the axis of symmetry. The value of p will tell you, which way to travel from the vertex to get to the focus. And the distance from the vertex to the focus is the same as the distance from the vertex to the directrix. And then to find those points at the ends of the latus rectum, just remember, and I'll write this down in the video, I wrote it in the last video as well, but the length of the latus rectum is the absolute value of 4p, right? So whatever this 4p is, that'll give you a hint as to how to find the latus rectum. The length of the latus rectum will be the absolute value of that 4p. Alright, so I'm just going to assume you've read through this now and just get into some examples. Alright, so in each example I'm going to be given an equation. It may be in standard form, it may not be. And if it's not in standard form, we're going to do something to put it in standard form. And then once it's in standard form, we should be able to graph the parabola, right? And in the process of graphing, identifying and labeling, the vertex, the axis of symmetry, the focus, the directrix, and also the endpoints of that segment called the latus rectum. Alright, so the first equation I'm given, the first example I'm going over, has a quantity with y squared equal to a number times a quantity with x. So this is in the standard form for a parabola. It's in this form. The quantity y minus k squared equals, some number 4p times the quantity x minus h. It's in that form there. So if it's in this form, again where the y is squared and the x is not, I know right away that when I draw this, the axis of symmetry which I'll abbreviate as AOS, like this, axis of symmetry. If the y is squared and x is not, the parabola is going to have an axis of symmetry that's horizontal. And if the axis of symmetry is horizontal, that tells me also that the directrix, there's another dotted line, another special line we're going to have to find called the directrix. If the axis of symmetry is horizontal, the directrix will be vertical. Because the directrix and axis of symmetry should be perpendicular. And same thing for that lattice rectum. The directrix, the lattice rectum, that special segment will also be vertical. It should be parallel to the directrix, perpendicular to the axis of symmetry. Now the vertex, again, once we have an equation that we know and recognize is in standard form for a parabola, the vertex has the coordinates h, k. So remember, h goes with the x. So you see x plus 3 here. But x plus 3 is the same as x minus negative 3, right? We want x minus h. So the value of h, the x coordinate of the vertex, is negative 3. And the value of k is the number being subtracted from the y when it's in standard form, y minus k, and that's y minus 1. Right, so the vertex of this parabola is negative 3, 1. Another way to think about h and k is what value of x and what value of y would need to be plugged in to give me 0 equals 0 when it's in standard form like this. So it would be negative 3 for x, 1 for y, I get 0 equals 0. And that's a true statement. This vertex is on the parabola. All right, and then off to the side here, I'm going to start drawing a very rough sketch of our parabola information on the xy plane. So negative 3 for x, 1 for y, and here is the vertex. There's the vertex. That point is actually on the parabola. And I said it earlier, the axis of symmetry when y is squared and x is not is a horizontal line. So draw a horizontal line through this vertex, and there's the axis of symmetry. And being a horizontal line, the equation is going to be y equals some number, and that's y equals 1. And it's just going to be y equals the y coordinate of the vertex. Right. All right, now I'd like to find that focus and directrix. So I need the value of this p. Well, this is in standard form. The negative 16 is what is equal to 4p here. So the value of p would be negative 4. Now if we're talking horizontal axis of symmetry, remember negative means like a negative change means go left. A positive means go right. So when I see p equals negative 4 here, that tells me that the focus is 4 units left because it's negative, right? left of the vertex. All right, so if I go from the vertex 4 units to the left, here's negative 7, 1, and I'll put this in a different color if you can make out the colors, because this is not on the parabola. The focus is not a point on the parabola. It's like surrounded by the parabola. The parabola curls around it. So the focus, I'll write the coordinates here, is at negative 7, 1. All right. Now this is again not a solution. If you were to plug in negative 7 for x, you'd get positive 64 on the right side of the equation. You plug in 1 for y, you get 0 on the left. You'd have 0 equals 64. That's not true. All right. So not a solution. And then if you know the focus is 4 units to the left of the vertex, that means the directrix, right, that special line, is 4 units to the right, and it'll be vertical, right, if the axis of symmetry is horizontal. So here's the directrix, and it's a vertical line, so x equals, and that's x equals 1. Right, that's 4 more than the x coordinate of the vertex, right? It's 4 units to the right of the vertex. Right, and now that I have the focus and directrix in, I should be able to find those ends of the lattice rectum. Now a note I made last time I'm going to make again here. The length of that segment called the lattice rectum is the absolute value of 4p. All right, so basically just take this, if it's in standard form, you take this coefficient of the expression on the right here, make it positive, that's the length of the lattice rectum, 16. And I'm going to cut this in half and use symmetry to find the points on the ends of the lattice rectum, which are also points on the parabola. They are solutions of the equation. And the lattice rectum and directrix should be vertical, right? They should be parallel. And I go from the focus, 8 units up. So from the focus, 8 units up. That takes me, from negative 7, 1 to negative 7, 9. And I'll label this, right? Negative 7, 9. That should be a point on the parabola. That is actually a solution of this equation. And check it out. Replace x with negative 7. You'd have positive 64 on the right side. Replace y with 9. You'd have 8 squared positive 64 on the left as well. That's a solution. And then from the focus, go 8 units below, right, 8 units down. And if I go from negative 7, 1 down 8 units, I'm at negative 7, negative 7. There's the other end of this segment that I'll now draw in called the lattice rectum. Right? The lattice rectum goes from one point on the parabola through the focus to another point on the other side of the parabola, and it's perpendicular to the axis of symmetry or parallel to the directrix. This is called the lattice rectum. This blue segment, this dotted segment. Again, that's not part of the parabola. It's just a dotted segment. Right, now that I've got all this in, the focus, the directrix, the vertex, the endpoints of the lattice rectum, the axis of symmetry, I got all the junk they wanted. Now I can make a rough sketch of the rest of the parabola. Right now I've only got 3 points on the parabola, the vertex and these 2 ends of the lattice rectum. Well, from the vertex, just kind of start making your parabola. Go from the vertex and make a curve that goes through the ends of the lattice rectum, and just make sure it gets wider as you get further away from the vertex. Right? So something like that, and little arrows on the end to indicate it goes in those directions forever. There's a graph of the parabola. Right, this parabola opening to the left. All right, and then why we found the focus and directrix? And again, I mentioned this in the last video when the vertices were at the origin. But why you find the focus and directrix is because of the definition of a parabola. A parabola is made up of points, and any of these points, take any point on the parabola, take the distance to the focus and the distance straight to the directrix, go perpendicular to it. Those two distances will be the same, no matter what point you're at. So here, from the point, now this one's an easy one. Take the point -7, 9. See how that's 8 units from the focus? And then it's also 8 units away from the directrix. The vertex is 4 units from the focus and also 4 units from the directrix. Okay. And that's the same for any point. If you were to find other coordinates of points on this and find the distance to the focus and then the distance, straight to the directrix, they'd always be the same distance. Right. That's why the focus and directrix are important. Okay, and then just to make sure that my graph here is correct, make sure the vertex, I just want to put this into a calculator, this equation, and I want to see if the vertex is correct and these 2 points are also on it. All right, just to double check. All right. So I'm going to that desmos.com, desmos.com, free online graphing calculator, and I'm going to enter the equation we were given, right, the quantity y minus 1 squared equals, -16 times the quantity x plus 3. Right, and you see they have there's the point 3, -1, clearly the furthest right point on the parabola, the vertex. And they also have the x-intercept. They always throw the intercepts in there. But you could find the x-intercept, right? Just replace y with 0 and solve for x. And I just want to make sure that those other 2 points we found were on there too. Well, I can probably just zoom in. -7, 9 should be on this. There we go, -7, 9. That was one of the ends of the lattice rectum. And so should be -7, -7. And that's on the parabola for sure. Right. So looks like the graph I drew is good. All right. Now, of course, all the other stuff isn't labeled in Desmos. The lattice rectum, the focus, the directrix, the axis of symmetry. That's all for you to put up. Great. All right, my next example is similar. It's another one where the equation is given to us in standard form already, right? The standard form is some quantity squared equals a number times another quantity, right? One with y, one with x. And once again, we have the equation where the y is being squared, right? Y minus k squared equals some number 4p times and then some quantity with x minus h. So just like in the first example, I can tell you right now that the axis of symmetry is going to be horizontal. Right? It's got to be a horizontal line, and that means that the directrix and the lattice rectum are going to be vertical. All right. Now, since it's in standard form, right, the vertex of this parabola should be simple enough. Again, just think about the value of x and the value of y that would make this 0 equals 0 once it's in standard form like this. So 8 for x and -1 for y. All right, so 8 for x, -1 for y. There's the vertex. And I'll start plotting this. All right, so here's and if you have graph paper, maybe that'll make it easier, but so make it nicer looking. I'll go to Desmos after this and we'll look at a nicer looking graph than my hand drawing. So 1, 2, 3, 4, 5, 6, 7, 8, and -1. Right. So here's the vertex. This is actually a point on the parabola. And the axis of symmetry has got to be horizontal. Right? So the horizontal line that goes through the vertex. So this line, this dotted line here. Right? There's the axis of symmetry, and it's a horizontal line, so the equation's y equals, and then it's y equals -1, right? The y coordinate of the vertex. All right, and then the focus is going to be somewhere on this line, either to the right or to the left. It all depends on the value of p. Right? So this time the 4p is +4. So the value of p is 1, and that's +1. So that means the focus is right 1 unit, right? When you're talking horizontal, right is positive, left is negative. Right? And when you're talking vertical, up is positive, down is negative. Right? But p is 1, +1, so the focus is 1 unit to the right of the vertex. There's the focus right there. Right, so I'll put that over here as well, the actual coordinates. The focus is at the point 9, -1. All right. And then the directrix is 1 unit to the left of the vertex then. So this vertical line at x equals 7. Right, here's the directrix. X equals 7. Right, it's a vertical line. All right, and now that I have all this stuff in, I should be able to find the points on the ends of that lattice rectum. So again, the lattice rectum length, the length of the whole lattice rectum should be 4, right? Whatever the absolute value of 4p is. Well, 4p is just +4 here, right? So I cut this in half and go vertically, right? So and then from the focus, right? So from the focus, I go up 2 units. So from 9, -1 to 9, 1. And then down 2 units, right? From 9, -1 to 9, -3. And those should be points on the parabola, right? 9, 1, 9, -3. Those are the ends of this segment called the lattice rectum, right? This segment containing the focus that's parallel to the directrix. And double check, make sure that 9, 1, and 9, -3 are actually solutions of the equation. If I replace x with 9 and y with 1, you'd get 4 equals 4, which is true. And replace x with 9 and y with -3, and you'd again get 4 equals 4 after simplifying. So those are solutions. And now that I have the vertex and these endpoints of the lattice rectum labeled here, I can make a rough sketch of the rest of the parabola, right, the rest of these points. And there you go. And once again, if you were to take any point on this parabola, that point there, say, the distance to the focus and the distance straight to the directrix would have to be the same, right, no matter what point you picked. Right. I'm going to stop drawing this distance thing on the next examples, but that's why the focus and directrix are there, just to remind you of the definition of a parabola. Right. The only points that are actually on the parabola are on this, U shape opening to the right here. All right, let me test it out just to make sure that these are correct. I'm going to enter the equation. So we were given y plus 1 squared equals 4 times x minus 8. Right. So here's the parabola over here. Vertex at 8, -1, it opens to the right. And you see how it has the point 9, 1 and the point 9, -3, right? Those are the ends of the lattice rectum. So it looks like the points are good, my parabola is good. It's a good picture. Great. All right, so now the first two examples had y squared but not x. Right, so the axis of symmetry was horizontal. The parabola opened right or left. In my next examples, we're going to have x squared but not y. like this. Right? So we have, again, this is in standard form. The standard form is, some quantity squared equals a number times another quantity. One with x, one with y. So this is in this form. The x minus h squared equals 4p, right? Some number 4p times the quantity y minus k. Okay, now this case, when the x is squared and y is not, the axis of symmetry is vertical this time. And if that's the case, that means that the directrix and the latus rectum, when we find those are going to be horizontal then. All right, and the vertex, again, should be simple enough. Just what value of x and y could you plug in to get 0 equals 0 when you're in this standard form? Well, you'd have to plug in -2 for the x to get 0 on the left side there, and then +3 for the y. So the h and the k are -2 and 3. Right. And I'll plot this. Start making my stuff, right? So -2 for x, 3 for y. This is actually a solution of the equation, right? That's the vertex. This time the axis of symmetry is vertical. So this line here, this vertical line, containing the vertex, and that would be x equals -2, right? It's just x equals the x coordinate of the vertex. All right, now the focus is going to be on this axis of symmetry, either above or below. And that's where the value of p will help us with, right? If p is positive, the focus will be above the vertex. If p is negative, the focus will be below. So here the 4p is -20. Right, so the value of p is -5, right? And again, this tells me that the focus of this parabola is 5 units below the vertex. So from the vertex, I go down 5 units, and here's the focus at -2, -2. Right. I'll write the coordinates over here, -2, -2. Now, as I've been saying, this is not a solution. If you plug -2 in for x and -2 in for y, you'd get 0 equals 100. That's false. But it just indicates to us, which way the parabola will be opening. It's going to open down around the focus. Right, and then if the focus is 5 units below the vertex, the directrix will be 5 units above the vertex, and also, horizontal, as I mentioned earlier. So here's the directrix. And it's a horizontal line, so y equals, and it's y equals 8, right, which was 5 more than the y coordinate of the vertex. All right. Now the lattice rectum length, right, the length of that segment, the lattice rectum, is going to be +20, right, the absolute value of 4p. Take half of this and it's going to be horizontal, go right and left. And it's got to be parallel to the directrix. So from the focus, I'm going to go to the right 10 units. And that'll take me to a point on the parabola. So from -2, -2, if I go to the right 10 units, that'll be at 8, -2. And then I'll also go to the left 10 units. Again, this is not a great drawing. The spacing's not amazing. And there we go. And these should actually be solutions of the equation, and you can check that out. 8, -2, and then the other end of the lattice rectum at -12, -2. And here's the lattice rectum, right? This segment through, from the starting from one point, going through the focus to the other point, and parallel to the directrix. That's the lattice rectum. And again, check it out. Plug in 8 for x and -2 for y, and you would get 100 equals 100, which is true. And the same thing for if you plugged in -12 for x and -2 for y, you'd have 100 equals 100. Alright, now that I have the vertex and these points on the ends of the lattice rectum, I can make a rough sketch of the rest of the points on the parabola. Right, so just fanning out here, curling out from the vertex through these points. There's your parabola opening down. Alright, and this time I'll leave it to you to check on Desmos. Right, just enter this equation and you'll see the vertex is at -2, 3, and that these points are on it, right? The point 8, -2, and -12, -2 should be on the graph as well, and it's opening down. Wonderful. All right, so my next example is another equation where x is being squared and y is not. But this is clearly not in standard form. This is clearly not in standard form. Now, because x is squared and y is not, I don't see any y squareds anywhere. The standard form we want would be this. We want the one I had in example 3. The quantity x minus h squared equal to some number 4p times some quantity y minus k. Right, we want this. Well, in order to get it that way, we're going to complete the square on the x terms. And you've seen me do this with ellipses and hyperbola equations. We've done a lot of completing the square. I'm not going to go into lessons on how to complete the square. I'm assuming you know how to do that. But in order to get the equation from this form to this form, I'm going to complete the square. I'm going to start by, there might be some more to do afterwards, but I'm going to start by completing the square on the only variable that has a square term on the x's. Alright, so since I'm completing the square on the x's, the only terms I'm concerned with are the x's, so I'm going to keep those on their own side, x squared minus 8x. And since the coefficient on x squared is already 1, I can complete the square. So I'm going to leave some space for that number I'm going to add to complete the square on the x's. And then I'm going to take the other terms that don't have x to the other side. So adding 28y. So I have positive 28y on the other side now. And then I would add 208. Okay, so we got this now. Now comes the completing of the square. Right, so x squared minus 8x, I would take half of -8, which is -4, and then square that, which is 16. Right? So I'd be adding 16, and don't forget to do the same thing to the other side. Right? It's an equation, you got to keep it balanced. Now the whole reason we add this 16 is so we get a perfect square trinomial, and now I can express this left side like the left side of the equation we want in standard form. This would be x, the quantity x minus 4 squared. And then the other side I have 28y plus, and then 208 plus 16 would be 224. Now I'm almost there. I'm almost there. Right, you see the left side is in that x minus h squared form, a quantity with x squared. The right side, I want a quantity with y minus k, just one y, not 28y. So it's very simple. Just factor out the 28 from the right side. So I have x minus 4 squared equals, and then when I factor out 28, right, you'll get your 1y, right, like up here, plus, and then 28, well, 28 times 10 is 280, and then I would need 56, two of these, so 28 times 8 would be 224, right, 160 plus 64. So 28 times the quantity y plus 8. Now we have the equation in standard form. Right, now we have the equation in standard form. In fact, I'll put this in a little box. Right. And now that the equation's in standard form, I can graph the parabola just like in example 3. Right. This is another one where x is squared, y is not. So the axis of symmetry will be vertical. All right. And in fact, I'll tell you right now, the axis of symmetry is going to be the line x equals 4. And it's just going to be x equals whatever the x value of the vertex is, right? We can tell what the vertex is also very quickly. X would have to be 4, and y would have to be negative 8 to give me 0 equals 0 in this standard form. All right, so I'll start drawing this, a very small picture over here. So 4, negative 8. There's the vertex, 4, negative 8. Sorry about the tininess of those numbers. And then the axis of symmetry is vertical, right? Because again, x is squared and y is not. The axis of symmetry is x equals 4. The value of p is 7, right? 4p would be this 28 here. So the value of p is 7, and that's positive 7. So that tells me the focus is 7 units above the vertex. So the focus is here. I just added 7 to the y coordinate of the vertex, and I'll write out what the focus is over here. Would be at 4, negative 1, right? Just adding 7 to the y coordinate of the vertex. And then if you subtract 7 from the y coordinate of the vertex, you get the directrix. Here's the directrix will be 7 units below the vertex and horizontal. Right? If the axis of symmetry is vertical, the directrix will be horizontal, and that's y equals negative 15. Right? And then those ends of the lattice rectum, right? Remember this 4p, the absolute value, which is 28. 28 is the length of the lattice rectum. You cut that in half is 14, and it's got to be horizontal. So from the focus, I go 14 units to the right. I'm just going to do this. 4 plus 14, that's 18. And then 4 minus 14 is at negative 10. And here are the points on the ends of the lattice rectum. One's at 18, negative 1. The other's at negative 10, negative 1. And here's the lattice rectum. Right. Again, you can double check that these are actually solutions of the equation. 18, negative 1, negative 10. Plug in, and you can even go back to the original equation. You should be able to plug in 18 for x and negative 1 for y, and you would get 196 equals 196. And then plug in negative 10 for x and negative 1 for y, and again you would get 196 equals 196 in the standard form here. Or back up here, you'd get 0 equals 0. You should anyway if the equations are the same. And now that I have the vertex and these points on the ends of the lattice rectum, I can draw a rough sketch of the rest of the parabola. And wonderful. All right, now this one, because it was so much different than the first three, I'm going to go to Desmos to double check my work. And the way I'm going to check it is I'm going to put in the original equation that wasn't in standard form, and I'll put in this equation we ended up with in standard form and see if that they're actually the same graph. And you'll see the vertex will be at 4, -8, and the point 18, -1 will be on it. The point -10, -1 will be on it. It'll be a parabola opening up. We'll see all that stuff. All right, so the original equation looked like this. It was x squared minus 8x minus 28y minus 208 equals 0, and you see this parabola. Right. And you see it's definitely got 4, -8 as the vertex, and the point, I'll actually plot the points that we said were at the ends of the lattice rectum, right? The point 18, -1 should be on this, and you can see that purple point that just showed up is definitely on the parabola. The point -10, -1 was the other end of the lattice rectum. That's also on the parabola very clearly. So that equation in standard form should definitely be the same graph, right? I had x minus 4 squared equals 28 times the quantity y plus 8. And you see it's right on top. Right, I can keep turning this off and on, and you'll see it comes right on top. It's the exact same graph as the original. So it did well. Great. And my next example is just like this one, but instead y is squared and x is not. But I'm still doing the same procedure, the completing the square, to put it in standard form. Right, so like I said, very similar to example 4, where the equation I'm starting with is definitely not in standard form. But I'm noticing the y is squared and there is no x squared. So that means we would like to put this in the following form, right? We want standard form where you have y minus k squared equals 4p times the quantity x minus h. I want to put it in this form here by completing the square on the y's. So the two y terms I'll leave on their own side, y squared minus 6y. And then because the coefficient of y squared is already 1, I'll leave some space. I can already complete the square. And then all the terms that don't have y in it, I'll take to the other side. So I'd be adding 8x and subtracting 1. So we have 8x minus 1 on the other side. Now to complete the square, I'd be adding 9 on the left. And so I'll do the same on the right, add 9. And then this y squared minus 6y plus 9 is now the quantity y minus 3 squared. Right, so the left side looks good. It looks like now I'm almost in standard form. The right side is 8x plus 8, right, which is not quite there. Right, I want 1x, not 8x. So I just factor out the 8. Right, so we have y minus 3 squared equals factor out this 8, and you have 8 times the quantity x plus 1. Now I have the equation in standard form right here. And once the equation's in standard form, I can do all the same stuff I've been doing, right? The vertex would be simple. Just pay attention to what's the x, what's the y. Too often people will just go left to right. The x coordinate for the vertex needs to be -1. The y coordinate for the vertex needs to be +3, right? So -1, 3 is the vertex. So here's the vertex. All right, then the axis of symmetry, it's going to be horizontal this time because the y is squared and the x is not, right? So the axis of symmetry is horizontal and it's y equals 3, just the y coordinate of the vertex. And then to find the focus, I find that value of p, right? Well, 4p this time is 8. So the value of p is +2. And when we're talking horizontal, +2 means, right 2. So if I go from the vertex right 2 units, I'm at the focus, right? And the focus here is at the point 1, 3. Right? From negative 1, 3, I go to the right 2 units, 1, 3. And then the directrix, I go from the vertex, I go to the left 2 units. And the directrix will be vertical. The directrix is a vertical line, x equals negative 3, right? 2 units to the left of the vertex. And then, 8 is the absolute value of 4p. That's the length of the lattice rectum. So I cut that in half, that's 4 units. So from the focus, I go 4 units up and 4 units down, and we get those points at the ends of the lattice rectum that are actually on the parabola. So here's 1, 7 and 1, negative 1. I'll label those. 1, 7 should be a solution. 1, negative 1 will be a solution. And then here's the lattice rectum here. And now that I have the vertex and these points, I can make a rough sketch of the rest of the points that are actually solutions, right? The rest of the points that are actually on the parabola. There you go, this parabola opening to the right. All right, and then once again, I'll check it with Desmos. And I think this might be the last one I'll check with Desmos. I got a few more examples, but I'll leave them to you. All right, so clearing all this out. Now the original equation we were given is y squared minus 6y minus 8x plus 1 equals 0. And you see the parabola showing up. Clearly the vertex is at negative 1, 3. And we should see the point 1, 7 on this, right? 1, 7. There it is. That was one of the ends of the lattice rectum, and you can very clearly see that's on the parabola. And the other one was at negative 1, negative 1. Right. There's 1, negative 1 also on the parabola, right, that other end of the lattice rectum. So it looks like we did good, or I did well. But let me just double check for triple check. I'm going to put in the equation we wrote in standard form, right, after I transform this to standard form. Y minus 3 squared equals 8 times the quantity x plus 1, and you see it's the exact same graph. You can turn it off and on and see that it comes up right on top of the other one. So, great. All right. Now this example, example 6, now this equation is already written in standard form. Right. Already written in standard form, where y is squared, x is not. You got a square equal to a number times a quantity without a square. Right. So I can tell you right now all the stuff, right? We can very easily get into this. The vertex will have negative 4 for the x coordinate and positive 2 for the y coordinate. Right, negative 4, 2. There's the vertex. Now the axis of symmetry, again, y is squared and x is not. So the axis of symmetry is going to be horizontal. The axis of symmetry is y equals 2. And the directrix will be vertical, right? And so will the lattice rectum. Now the value of p, right, 4p is this coefficient over here, 4/5. And if I just divide both sides by 4, or multiply both sides by 1/4, you see that p is 1/5, right? P is a fraction this time. But it is positive. So that means, maybe I should have made these notches bigger, but that just means that the focus is 1/5 of a unit to the right of the vertex. All right, so the focus would be at, this is at negative 4, 2. If I move that to the right 1/5, that'd be negative, that's negative 20/5. So that'd be negative 19/5 for the x coordinate of the focus, and then the y-coordinate is of course still 2. And then the directrix would be 1/5 of a unit to the left, so negative 21/5, and vertical. So here's the directrix. And it's a vertical line, x equals negative 21/5. Again, only 1/5 of a unit to the left of negative 4, to the left of the vertex. And then eep. Again, the 4p, this is the lattice rectum length, right? The absolute value of 4p, but it's already positive. So cut that in half is 2/5, and the lattice rectum will be vertical. So this is what, 2 is the same thing as 10/5. I go up 2/5 to 12/5, down 2/5 to 8/5, and there's the points on the ends of the lattice rectum. Again, yikes, I'm sorry about the, maybe I will go to Desmos for this one to verify things. But let me put this here, the end points of the lattice rectum. One of them is going to be at, it's going to be 2/5 above the focus, so negative 19/5, comma 12/5. And that's actually a point on the parabola. That's actually a solution. If you were to plug in negative 19/5 for x and 12/5 for y, the equation would be true. The other one's at negative 19/5, comma 8/5. Right. And then once I have the vertex and these points on the ends of the lattice rectum, and I can make a rough sketch of the parabola. Alright, because all these crazy fractions showed up, I'm going to verify it in Desmos. I know I said I wouldn't, but I don't like the fact that there's all these fractions here. So let's go back to Desmos. I'm going to enter the equation we were given. Right, the quantity y minus 2 squared equals 4/5 times the quantity x plus 4. Yeah, parabola for sure. Opening to the right. Vertex is at negative 4, 2, which I had written down. And then I just want to make sure that those points I said at the ends of the lattice rectum are also on this, right? So we had negative 19/5, comma 12/5. And yeah, you can clearly see that that is on the parabola, right? It's really close to the vertex, but if you zoom in, you can make it look as far away as you want. But there's, negative 3.8, which is negative 19/5, and 2.4 is 12/5, right? So I'll keep that labeled. And then the other one was negative 19/5, or negative 3.8, comma, then 8/5, or 1.6. Oops. Label that, right? And these are clearly on the parabola. Right? They are solutions, and they're directly across from each other. And if you drew a segment connecting them, the point halfway in the middle would be the focus. The focus at negative 19/5, comma 2. Yeah. All right, so that was good still. All right, even though the fractions do come up on occasion. All right. This next example is another one of those where it's not in standard form to start with. All right, but I can do some completing the square on the x's here because there's an x square but not a y to get it in standard form. All right, so I'll keep the x terms on their own side because we're going to complete the square on the x's. And then add the 4y, subtract the 95 on the right. Now the lead coefficient of the x squared here is not 1, it's 3. So you could do one of two things. You could divide everything by 3. That's going to throw some fractions over here. I don't really care for that right now. Or we can factor 3 out. I'm going to factor 3 out first from the x terms. So we have 3 times the quantity x squared plus 10x. And now I can complete the square. So I'll leave a little space, close the parentheses. We're going to complete the square inside this set of parentheses here. And then the other side I haven't touched yet. All right, and then when we complete the square, you got to remember what you factored out, though. All right, so I'd be adding 25 in here, okay? But remember, we pulled out a 3 earlier. 3 times 25 is 75, so I'm going to be adding 75 to the other side to keep it balanced, right? This is the 25 I added in the parentheses, but then multiplied by the 3 that I factored out. Don't forget that. All right, so now the left side is 3 times the quantity, x plus 5 squared equals, and then this side, when I add 75, this would be 4y minus 20. All right, negative 95 plus 75 minus 20. And then I factor out a 4. And we have 4 times the quantity, y minus 5. All right, then I'm almost done. All right, because remember, in standard form for a parabola, that square needs to be alone. So then I just simply divide by 3. So we have x plus 5 squared equals 4/3 times the quantity y minus 5. And there's the equation in standard form. Now that it's in standard form, I should be able to graph it pretty easily, just like all the other examples. The vertex would have negative 5 for the x coordinate, positive 5 for the y coordinate. So negative 5 for the, oh actually, you know what? I'm just going to do this. Here's negative 5, here's positive 5. So there's the vertex, because this one will involve some fractions again. The axis of symmetry is going to be vertical this time, right? Because x is squared and y is not. So the axis of symmetry is x equals negative 5, and then the directrix and lattice rectum will be horizontal. The value of 4p is 4/3, right? So the value of p is 1/3, and that's positive. So the focus is 1/3, so it's 16/3. It's 1/3 of a unit above this vertex. All right, so the focus is at the point negative 5 comma 16/3, right? That's 1/3 above 5. And the directrix will be 1/3 below, right? And horizontal. There's the directrix. And that's horizontal line, so y equals, and then y equals 14/3, right? 1/3 of a unit below the vertex. And then 4/3 is the length of the lattice rectum, so I go 2/3 right, 2/3 left. So here's negative 13/3, because this is negative 15/3. Go 2/3 right, 2/3 left, negative 17/3, and we go from the focus, 2/3 right, 2/3 left, and there we go. There's the ends of the lattice rectum. And I'll label those points too. I'll write them down here. I'll say the ends of the lattice rectum are at the points negative 13/3 comma 16/3 and negative 17/3 comma 16/3. And you can check. You can actually check that these are solutions of the equation we're given, but I'll leave it to you to check. Right? So again, all the same stuff. Vertex, axis of symmetry, then you should be able to find the focus and directrix, and then the points on the ends of the lattice rectum, and draw a rough sketch of the parabola. Okay, and I've got one final example with basically the same procedure. All right, I have this equation that starts off definitely not in standard form. I notice that y is squared, there is no x squared. Y is squared and x is not, so this will be a parabola opening to the right or to the left, we'll see. And I'm going to complete the squares on the y's. Right, so keep the y terms on their own side here. So I have 3y squared, and then there's negative 6y. And then take the other terms without y to the other side. I'm going to add 4x, and then subtract 23. And then just like before, I'm going to factor a 3 out of the y terms so that I can actually complete the square on the y's. And then when I complete the square on the y's, you have to add 1 in here. But if I add 1 in here, remember I pulled the 3 out earlier, that's 3 times 1, that's adding 3. So I add 3 to the other side. And then I have 3 times the quantity, y minus 1 squared equals, and then this is again 4x minus 20, right, after I add 3. Pull the 4 out, we have 4 times the quantity x minus 5, and then just divide by 3 now to get the square alone. So we have y minus 1 squared equals 4 thirds times the quantity x minus 5. So here's the equation in standard form, very similar to the last one. The only difference being the vertex is at 5, 1 instead of 5, negative 5. The vertex would have an x-coordinate of 5, a y-coordinate of 1. Making a rough sketch over here. So again, just here's, say that's 5, and this is 1. Or sorry, this is 1, that'd be negative 1. 5, 1. There's the vertex. The axis of symmetry is going to be horizontal this time, because the y is square, but the x is not. So this time the axis of symmetry is, y equals 1. The value of p, right, well 4p would be this 4 thirds. So p is, again, positive 1 third, meaning that the focus is 1 third of a unit to the right of the vertex. So that's 15 thirds. 1 unit right would be 16 thirds. Right. So here's the focus. Right, so the focus would be at 16 thirds, comma 1. Right. And the directrix would be a third of the unit to the left of the vertex. So, and vertical, right, because the axis of symmetry is horizontal. Here's the directrix. X equals 14 thirds, that vertical line. And then again, the absolute value of 4p would be 4 thirds. That's the length of the lattice rectum. So I cut that in half, go 2 thirds up, 2 thirds down. So up is 5 thirds from 1, and then down is 1 third. I go up 2 thirds. That's a distance of 4 thirds there. And then we get some points on the ends of the lattice rectum. And we can draw a rough sketch of the parabola. Right. Opening to the right like that. And I'll write out what those ends are. Right. The ends of the lattice rectum would be the points 16 thirds, 5 thirds, and 16 thirds, 1 third. And once again, I leave it to you. I'm going to leave it to you to check that these are actually solutions of the equation. All right, and then, check the graph as well. All right, so that was a lot of the same. All right, some equations were in standard form to start, some equations were not. We had to complete the square, on one of the variables to put it in standard form. But once you got it in standard form, you should be able to easily identify the vertex, the axis of symmetry. Once you got those, then find the value of p, and then you'll know where the focus and directrix are. And then take the absolute value of 4p, cut that in half, and that'll tell you how to get from the focus to those endpoints of the lattice rectum. And then once you have the points on the ends of the lattice rectum and the vertex, you can make a rough sketch of the parabola, as I've done with all these examples. All right. And I really hope that watching me go through these 8 examples helps you in some way when you're trying to graph a parabola whose vertex is not at the origin on your own. And thank you very much for watching.